Good afternoon, everyone. This is Ankur. Thank you for joining. We welcome you to this series of webinar, monitoring and ventilation. As you're aware, with respect to the time we are in, this is one of the most relevant topics which a lot of our organizations and customers are looking for. And we thought it would be really great for us to walk you through this small presentation. At TI, we are really proud to be able to partner our customers in this time of need and offer solutions for such critical applications. So we'll have two sessions. First presented by Sanjay Pitharia, which will be on patient monitoring. And then we'll have the second one presented by Sanjay Dikshit on respiratory machines. So each one is session is half an hour, and we will have a Q&A at the end of the session. So there is a chat window enabled on all your screens. You can send in your questions to us in this window, and we'll answer as much as possible towards the end of this presentation. If there are further questions and you would like to have further details, you can send us a note in the chat window, and we'll get back to you after the session. Sanjay, I invite you to present on patient monitoring.
Thanks, Ankur. So, hello everybody. I am Sanjay Pitharia. I am systems engineer here at Texas Instruments. So, I will be focusing on patient monitoring, and then we will have another session on ventilation. So, here is the agenda for the first session. We will start with an introduction to TI's classification of medical sector and talk about the market trends in patient monitoring. And then I will talk about the challenges in measuring ECG and PPG or SpO2 measurement with temperature monitoring. And then lastly, we will discuss about TI's subsystem level reference designs, which can help in prototyping and reducing the overall design cycles for our customers. So TI semiconductors are supported in every medical category, and TI actually divides them into 5 different categories: medical imaging, patient monitoring and diagnostics, medical equipment, home healthcare, and personal care and fitness. Medical imaging consists of ultrasound scanners, X-ray machines, MRI, CT scanners, PT scanners, and these are all big machines and help with some image of the patient. Patient monitoring and diagnostic category takes care of all the vital signs sensing and monitoring. If we consider patient monitoring category as a category which takes human vital signs as inputs, then medical equipment is a category which mostly involves all the output devices like ventilators, infusion pumps, anesthesia machines, like that. The home healthcare and personal care and fitness, these are mainly used at the not at the hospital. So home healthcare takes care of blood glucose monitors, CPAP machines, nebulizers, oxygen concentrators, and the personal care and fitness typically includes wearables, treadmills, or beauty and grooming, shavers, groomers, all those. So in this presentation, as I have highlighted, we'll be talking about patient monitoring and diagnostics. So patient monitoring is not new. It's been for a while, but there are a lot of new trends are coming. The market is growing. For example, the growing elderly population is driving a very high demand of remote monitoring. For example, in Europe, around 700 billion euros are being spent every year on chronic diseases. And the advantage with remote monitoring is that it enhances the quality of care. It reduces overall healthcare cost while providing mobility advantage to the patient. So patient can wear it and move around. Now, wearable wireless medical technology enables accurate and reliable data in a small form factor. But then there are some challenges which needs to be addressed. So the challenges are it should support different modalities or the different vital signs. It should have longer battery life because it is all operated on battery. And there is something called ship mode, which I'll be covering in one of my slides, which is also an important factor to improve the battery life. Once the vital signs are monitored and captured and sent for the processing, artificial intelligence uses analytics and big data to improve decision. decision making and early prevention. So it is these are all big trends coming in patient monitoring. So if we go into the details of this new trends and what TI is doing, what Texas Instruments is helping in terms of small subsystem reference designs, I would like to just briefly talk about some of the parameters. So there are two main parameters we'll be talking about. One is called ECG or electrocardiogram. It's actually a measure of electrical activity of the heart, and the second one is called photoplasmogram, which is PPG, or it's an optical measurement of an organ's volume. So its ECG is physical or an electrical information about heart, whereas PPG is optical measurement of particular organ's volume. And that's the circuit for both of these are different because the signals are in nature different than each other, right? So going into much detail, if we compare these two, then what we have is ECG is electrical signal, as I mentioned, and PPG is optical measurement. But ECG needs some kind of electrodes, so they have to physically be connected to the body. And for PPG, we need an LED and a photodiode. Both of these can be used for measurement of heart rate because ECG and PPG both have same frequency of operation. So the timing wise, both are able to give heart rate calculation. Both can give diagnostic information, but depending on how much detail we can get from ECG and PPG, and depending on number of electrodes, number of leads, the information will vary. The number of skin contacts, the minimum number of skin contacts required for ECG are 2, and it has to be across the heart. Typically, it is across chest, but it can be also measured from one hand to another hand. But it should complete the path through heart. Whereas PPG is standard PPG or the SpO2 is a finger clip type, which you see in the hospitals. So that one uses a transmitter and a receiver. There are newer devices coming with which can be worn on wrist, or it can be worn on forehead, ankles. So there are different ways to measure, and that's called reflective type of PPG. And depending on how many contacts are there, how many sensors are there, the number of ADC channels will vary. With now, let me show the frequency domain characteristics of both of these. So now if we look at this graph, the AC component basically, then AC component of ECG is relatively low in frequency. It is usually between 0.05 hertz to maximum 150 hertz. And there are some diagnostic quality ECG which may require up to little bit higher, and what we see is 150 to 200 hertz. But then most of the ECG can come under 100 or 120 hertz. There are other biopotential measurement like EMG, which is electromyogram muscle information. There is EEG, which is related to the measurement of signals coming from brain. There is respiration, which is the breathing cycle, which is 0 to zero point 0.4 hertz typically. And some of the patients also have pacemaker signal, which is a little bit higher because that signal is a high frequency signal compared to ECG. And on the y-axis, we are showing signal amplitude. So all these signals are typically less than 10 millivolts. And that is why the signal conditioning circuit is very important for this kind of applications. Now, measuring ECG and PPG, there are a few challenges involved in this. And these challenges come from different sources. So for example, ECG measurement is happening, then our body is a floating antenna, and it can catch signals from 50-60 hertz lines which are there at our home, at hospitals, or at our working environment, right? So this AC 50-60 hertz pickup is actually creating power line interference in the measurement of ECG. And what you see is this signal is little bit dark. It's not a clean signal that is coming because of the line pickup. The second is something called baseline instability. This comes because of poor electrode connections. If the connections, the electrodes are not connected properly to the patient, then it can be seen that the signal will vary uh, in the amplitude, and it will not give proper signal. Right? Sometimes what happens is there are applications where ECG measurement is happening, but then person is also moving, and there is also like, for example, if it's a watch kind of application, a person is walking or running, then there is muscle shaking, and that can create a problem in the DC level shift uh, of the baseline. So that is also called wandering baseline or DC shift. So all these measurement challenges have to be taken care uh, either in software or hardware by the designer, and that is actually becomes sometimes a design challenge for the user. Now, if we look into the PPG or SpO2 measurement or optical biosensing, again there are also some design challenges involved. For example, typical optical biosensing is battery operated. So again, low power for longer battery life, which is also true in ECG case. There is skin tone variation. There are people with a little bit dark skin. There are people with fair skin. There are people with a lot of melanin in their body. So the skin color will vary, and this skin color will decide the amplitude of the signal. So that's why it has to be taken care. There is also, as I mentioned, motion. People are running and measuring the heart rate. So there has to be motion cancellation algorithms involved. Um, as I mentioned earlier, this is LED and photodiode. So there is a glass involved which will be used for measurement, or sometimes lens or glass. So it should also not um, come in the measurement area, so that the measurement is very clear. And finally, the ambient light. When we are measuring this signal, we have to make sure that the ambient light is not creating any issues for this biosensing optical measurements, right? So now, with these challenges in mind, I would like to just show what TI is doing in medical. So if you go on ti.com, you will see there is a section called applications and designs, or applications. And in that, there is a section where you can see medical as a sector. And within medical, there are these 5 categories, which I already mentioned: the imaging, patient monitoring, home healthcare, medical equipment, and personal care and fitness. And each of these have some kind of medical product. You can see ultrasound scanners, ECG machines, pulse oximeter, ventilator, all this, and all these are clickable. So for example, if I click on medical sensor patch, what I see is I will see a description where I am highlighting a few challenges in this particular product, and then it has some block diagram. This block diagram is a standard block diagram. It is not specific to any particular of our customers. It's a standard block diagram. You may or may not have all the blocks in this in your system, but this is showing kind of a superset. And what you can do is you can click on one particular block, which will show you some products from TI and some reference design from TI. I will talk about the reference designs, but products are uh, TI has products in all analog, embedded processing, power, signal chain. So it will show all the products, and it will also show some of the reference designs. Yeah. So for example, on the left side, what I show is some of the products. So you can see that there is a TMP117. It's our plus minus zero point 0.1 degree C accurate temperature sensor. And on the right side, what you see, there are some biosensing AFEs. For AFE, for measuring the optical measurement, heart rate monitoring, or there are some other AFEs, right? So all these products are available when you click on that block. And to highlight on the reference design, this is again another example, which is for multi-parameter patient monitor. It is showing some For this block, it is showing some reference design. It is a multi-parameter patient monitor for vital sign measurement. So what is this reference design? So reference design is not an EVM. Most of you are maybe aware that TI has a lot of evaluation modules called EVMs, which are very specific to a product. Maybe it's an ADC EVM or a microcontroller EVM. Reference design is actually combination of multiple devices, and it comes with not only the design, it comes with lot of calculations or how we have selected the components, full schematic layout, Gerber files, sometimes spice simulation. It comes with some testing done. We do test this PCBs at our end, and we actually do some measurements and put all the results in the design guide, and the design guides are also available on ti.com. So you can note down the number of the particular designs which I will talk. I will take 3 examples here, and then you can go to ti.com and actually go into details of that particular design and find that everything is available for you to take care. The only thing is these boards are not sellables. These designs are not sellable. So TI doesn't sell these designs. TI doesn't have many of these boards, but Gerber files are there. You can take the Gerber files and build your own boards. Everything is available on ti.com. So I will take, as I mentioned, I will take 3 examples here. The first 2 examples are for the patch reference design, and third is a portable patient monitor reference design. So the first one is called TIDA-01580. It's a wearable wireless multi-parameter patient monitor reference design. What this design is actually measuring two things. It is measuring ECG and PPG. So TI has an AFE called AFE 4900, which can do synchronized measurement of PPG and ECG. It measures the signals and sends to a microcontroller, which is including an RF front end. So it is CC2640R2F. It's an MCU with RF, and it can send data over Bluetooth low energy. So whatever data is measured here, ECG and PPG, are captured by this device and sent over Bluetooth low energy to a remote terminal. And this board also is powered using a coin cell battery. So you can see on the left side there is a holder for that. It can measure all the data using a coin cell battery, and there is some power management circuit also available. So for the LED driving, you need boost circuit. For powering this microcontroller and this AFE, you need buck boost circuit. So everything is there. An entire board is available for the Gerber files are available, and you can actually build this and test this. Just for the reference, how we have tested this board. So this board has 2 electrodes. One is on the bottom and one is on the top. So on the bottom side, there is a metal contact with a window in the middle. That window is open for the PPG sensor, for the LED and photodiode, and this metal contact is used for ECG measurement. So what happens is the bottom electrode is connected to the left side, let's say for a left side of the left hand of the person, and right hand is connected on the top metal contact. Then it actually completes a path from left hand to the heart to the right hand. So it can actually measure ECG. And then if you put your finger or the wrist below this particular window, which is for the photodiode and LED, you can actually get PPG data. So what on the right side, what I'm showing is the receive side, where we have a launchpad from CC2640R2F. It's an EVM. It is receiving all the data which was sent by this design, and it is showing the data on a GUI. The GUI is also available for you to download, and it is available in LabVIEW. So we have tested this for PPG and ECG. The only thing is there are no algorithms involved here. We have done very basic filtering, but because TI is not a software company, we have not done any algorithms here. And it has been tested for 100 hours of continuous operation. CR's 3032 battery. It's a coin cell battery. And with a duty cycle of 1 second per minute, the battery life is calculated to be 30 days. So the battery is a disposable battery. So once you drain this battery, you have to just throw it away. So I will just highlight a couple of things here. So as I mentioned, it can do multiple measurements. It can do ECG and PPG measurement. There is something called pulse transit time, which is a difference between the peak of PPG and peak of ECG, and that can be used for some blood pressure calculations. We have not done any calculations, but we are giving raw data, so you can actually put some algorithms and do these calculations. So this is first thing. The second thing is that in spite of BLE being on the BLE connectivity being on the board, we have taken care of lot of layout related issues, lot of like common mode signal filtering. We have put chokes on that. The ECG front end and the Bluetooth low energy device, these are on different layers. So they are making sure that we have enough layers in between ground layers and power layers to make sure there is no interference, and we have good signal capture from this reference design. And then third one is extending battery life. So battery life, though this design has only coin cell battery, but there are some applications you might use rechargeable batteries. So in that case, right power architecture has to be selected. You should select right buck converter, boost converter. You have to put some devices into sleep mode, some into shutdown mode. So there is an application report which is available on ti.com. It's called improving battery life in wearable patient monitors and medical patches. So this we will be sharing all these slides with you, so you can go and click on this link, and then it will show you a good document which highlights what are the different ways to improve the battery life. Right now, the second, so this was the first design for ECG and PPG. The second design is on skin temperature measurement. So there is a design called TIDA01624. It's again Bluetooth enabled, a very high accuracy skin temperature measurement design, but this is done on flexible PCB. So the PCB is flexible in the sense that you can actually stick it to the human body. It will take the shape of the human body wherever it is connected. Let's say if it is connected on the arm, then it will take the shape of the arm. If it is connected on the chest, it will be shape. It will take the shape of the chest. Even the battery used, the silver battery, what you see here, that battery is also flexible battery. So and this has two devices. One is our latest device TMP117. It's actually a plus minus zero point 0.1 degree C accurate temperature sensor. And there is another device CC2640R2F, which is again the same device used in the previous reference design. And this sends data over Bluetooth low energy, and it can be captured over iPhone, iPad, or any remote terminal. So the softwares are also available on ti.com. You have to just search for TIDA-016244 for this. Just to highlight this device, TMP117, it's an ultra high accuracy digital temperature sensor, and the without even doing the calibration, we are able to achieve plus minus zero point 0.1 degree C accuracy in the human body temperature range. So you can look at this specs for this. The third design is for a portable patient monitor. So this is a design which is actually measuring ECG, PPG, heart rate, respiration, temperature, everything on a small mobile kind or a cell phone size PCB. So this is a very small portable unit which helps customers to move around, or our patients to move around by maybe putting it on the waist or putting it on the arm. And this is kind of a portable patient monitor. What we see in the hospital is bedside patient monitor, which is like very high end, but this is a portable patient monitor. And this, just to highlight on the block diagram, this has an ECG measurement chip ADS 1292R, which is ECG and respiration measurement. There is AFE 4403, which can do SpO2 measurement. There are three temperature sensors, again TMP117, which we have used for if you want to do multiple measurements at different places. Let's say at the chest and then leg or hand or forehead. You can do multiple of them. So 3 temperature sensors are used, and this is everything is operated on a rechargeable lithium ion battery. So you have entire power tree, which is making sure you have all the rails, charging of the battery and everything. And the raw data is available from an MSP432 device over an isolated 232 device. So you can actually get all the data over UART, and you can process it. You can put algorithms on that. And then what we have is, let me show you the GUI. We have a graphical user interface which can show the ECG, which can show the PPG, temperature readings, and respiration readings, everything available on the GUI. So this design is also TIDA-01614, which is available on TI.com, and all the Gerber files, software, design guide, everything is available with schematic layout on TI.com. So I talked about 3 designs. Now I want to highlight on 2 different topics. There is something called ship mode. So whenever, let's say, a manufacturer manufactures a battery operated system, what they do is they actually put the device into ship mode, so that when it goes to the retailer and from the patient will buy from them, it should make sure that the battery doesn't drain in between, right? So there is something called ship mode where they will electronically disconnect the battery from the entire load, right? And there are like load switches and everything available, but TI has come up with a different way where we are actually using 2 LEDs, one green LED and one red LED, to put device into ship mode and bring it out of the ship mode. So if you put a mobile or torch light on LED 1, it will go into ship mode, and if you put light on second LED, it will come out of the ship mode. And this entire circuit is taking less than 10 nanoamperes current. So these are all available for all small patches, glucose monitors, hearing aids, wherever you need ultra low power circuit. This can actually help. And the last one is about an overall system. So if we, let's say we have a nurse station or doctor's office and there is a patient monitor, so the patient monitor can actually communicate with all the patches over Bluetooth, and it can process the data and also communicate with the nurse station or doctor's office through a Wi-Fi. So TI has solutions for Bluetooth low energy. TI has solutions for Wi-Fi, and these are all available within different devices. So we have ultra low power, low energy Bluetooth devices. We have Wi-Fi modules. We have devices which can do both Bluetooth and Wi-Fi. It's called dual band devices. The devices are very secure, have with the FIPS 140 level 1 validation, and there are newer devices available with crystal-less. So if you many devices, microcontrollers need crystal, right? So these are called BOW technology, which there are a lot of new things have come where you don't need crystal. It is actually crystal-less, and it saves the area where you are talking about very small patient monitors or patches. So regarding the software, there is Simple Link is a TI's trademark where you can actually invest it once, buy maybe software kit for this, and then you can reuse the code between Bluetooth, sub 1 gig, Wi-Fi, Zigbee, and all the standards. So this was my last slide. There are 2 things. One, you can send your questions to Ankur, or you can send over chat box. And if you are also looking for some more technical questions and answers, you can go to TI E2E community, and you can find more answers on, right?
Um, so, times right now are very bad, and as everybody knows, for the COVID, the crisis, coronavirus, and there's a big requirement worldwide for ventilators, and many companies are looking to make ventilator solutions in order to somehow help with this situation. And with that in mind, we've got a presentation which is really around flow sensing, which is an important component in a ventilator. So I'll run through this presentation. To begin with, I'll just move down my presentation a little bit to for all those who are not very familiar with ventilators. I'll just talk for 5 minutes about a ventilator. So a ventilator is really a device which is meant to give respiratory support to a patient, and that's really, it works as in the form of an artificial lung, and it pushes air into the lung, and when a person has breathed, the air is pushed out of the lung back into the atmosphere. A ventilator really has certain mechanisms by which it does this. And the way this right now is a block diagram of a ventilator from a company who's released a design on the Medtronic. And essentially, a ventilator can take in the air from the atmosphere, and it can also take oxygen from a hospital oxygen supply. Now, typically what's done is that if you don't look at the oxygen for the moment, the air is just taken from the atmosphere through an inlet filter, very much like, it's like the way our air conditioners draw in air. But then inside a ventilator, they have some method of creating pressure with the air. Now, one way of doing this is really that you take a motor and you rotate the motor around in high speed, and that circulates the air in a circular manner in a turbine, and you can create pressure. And so now the air with pressure is given into an inspiratory block, which then from where it moves into outside the ventilator, where it goes into a patient mask. And within an inspiratory block, it's very important in the ventilator to be able to sense the pressure of the air, the pressure in the pipe, and the volume of flow in the air. So these are very important because, and our components. In addition, a ventilator really has another sensor which measures the barometric pressure, or that means the atmospheric pressure in the air. So the air from the turbine moves into the patient, and on the way to the patient, there is a oxygen sensor which measures the amount of oxygen in the air. And in ventilators, you can somehow set these settings so that you can give a certain percentage of oxygen into the air, maybe 95% oxygen, by looking at this sensor, and they can add in pure oxygen in order to achieve a certain percentage of oxygen delivered to a patient. When a patient breathes out, his air goes into what's called an expiratory block, which also has got a flow sensor, and it's got an expiratory valve, which is really a method which is a blocking arrangement to prevent air from the lung to completely escape to the atmosphere, because they like to maintain something called a PEEP setting, which is a minimum pressure in the lung at the time of expiration. So there's a valve which can block the complete release of air from the patient into the atmosphere. A ventilator has, of course, to measure all these things, to run the turbines and so on, has got a CPU, it has a fan. It goes up so because it's life and taking range, this is very important. Also, some alarm is triggered. So a loud buzzer must ring so that the patient is alerted. On the topic of ventilators, there are a lot of companies who are now worldwide trying to make simplified forms of ventilators. And this because in a professional ventilator, the pneumatics, the pipes, the whole system is pretty complicated, and there are a lot of companies who are trying to make these simplified ventilators, which are called balloon ventilators. And essentially, a balloon ventilator uses a kind of a disposable hospital supply, something which is used in hospitals, disposable, which is called an ambu mask. So people who need artificial support, life support, and in a hospital, generally you can get it in the hospital facilities. It's like a bag with a mask on top of it, and the mask is placed on your face, and a patient giver, a caregiver, presses this bag with his hands in and out. Now this bag basically is just a one-way valve, and it takes an air inlet from the atmosphere. So when you press in, the air from the atmosphere is delivered into the patient, and the patient inhales the air. When he exhales, the air goes out through a hole in the mask, and the bag itself again draws in air from the atmosphere and opens out again. So this way they can give artificial ventilation. So many people are trying now to make these ventilators which don't give this artificial ventilation by hand, because it's not possible to do it, but rather they think that they can put a kind of a motorized arrangement and around this. So you can have a couple of motors or even a single motor with some kind of a flap, and this flap can periodically keep on pushing the bag in and out to give this forced ventilation of air to a patient. Now, this can be done at a certain rate, which can be programmed by a user. And this rate is generally called the respiratory rate of the system. So it can be, we want to give 10 breaths a minute or 20 breaths a minute, so you can give it on a panel. And you can also define whether you want to do this ventilation for a child, an infant, or an adult. And this is very important because, you know, if you blow this bag in with the motor very hard, you can put in a lot of air to the patient. And if it's a baby, you can damage the lungs of the baby. So they like to give a control so that you do this softly. And a third thing which is which can be done, and I'll come to that a little bit later. Within this basic ventilator, you really have some kind of a system which may have a MCU which is driving a motor, which is pushing this out at a certain rate. And you can control the timing of the motor so that this bag is pushed, the motor moves in slowly or moves in hard, so that you can control the strength, as I was talking about, of the air which is blown in. But this is not very accurate. So what can be done in such a ventilator is that on the pipe leading from the output of the balloon into the patient, it is possible to put in a flow sensor. So you can put in a flow sensor, an airflow sensor of some kind, and the airflow sensor monitors the volume of air which is fed into the patient. And you can monitor this volume and then accomplish somehow a kind of a feedback loop, which sets a certain predefined volume as per a setting that you might have. So for an infant setting, you can have a smaller volume, but it's very accurate. And if anything goes wrong in the air being delivered, you will immediately know from the reading of the flow sensor. So you can trigger an alarm. Another very important thing in ventilators is that ventilators, professional ventilators, have two modes. One is called a spontaneous mode, and the other mode is called a mandatory mode. In the mandatory mode in a ventilator, the air is given a fixed number of times per minute, irrespective of the patient's interaction. So you can be unconscious and they'll be giving you a fixed number of breaths. In the spontaneous mode, a person's breath, the onset of inhalation, is used to trigger a breath. So for example, if a person tries to breathe, the ventilator, through the flow sensing mechanism, can sense the advent of breathing. And in doing so, the ventilator will sense a person is trying to breathe, and just like a power steering in a car, the motors will push in trying to drive a breath. So this is a second thing that can be done with ventilators, the making of a spontaneous mode. And it's very important, this mode, because it helps to wean patients off ventilators. Because if you don't have a spontaneous mode, the body gets used to mandatory ventilation. And the third thing, which is also now gaining importance, and I'll talk for a moment about it, is that you may want to add in to the ventilator oxygen from pure oxygen into the ventilator, into the ambu bag from an oxygen supply. And this can be done in conjunction with a finger clip sensor, an SpO2 sensor, the kind which Sanjay just talked about. So you can have within the system an SpO2 sensor, and an SpO2 sensor sees the oxygenation of the blood. And you can say that, okay, if we need a certain oxygenation, you look at the finger clip sensor setting, and accordingly, oxygen levels can be added into this ambu bag so that you achieve a certain setting of oxygenation into the blood. So this is more or less about ambu bags and balloon ventilators. And I can now probably go up and start talking about flow sensing, which is an important requirement in a ventilator. So a typical ventilator takes in air from an external source. They always have a flow sensor which measures the airflow from the air. They also have a separate pressure sensor also, but they mainly have a flow sensor, goes into the patient, and the air coming out of the patient also faces a flow sensor. And there are I talked about oxygen therapy a moment ago, which uses a finger flip sensor and can also use an oxygen concentration sensor. And you have another respiratory kind of machine, which is a CPAP machine, which also uses a flow sensor for its operation. It's very important to recognize why a flow sensor is required in the ventilator and why a pressure sensor is required in the ventilator. Actually, both are required. And as I mentioned, two flow sensors are required in a ventilator, one for inhalation and another for exhalation. And in inhalation, during inhalation, a control loop is established in a ventilator, which is called a volume control loop. It delivers a controlled amount of volume to the patient. And this is the setting I was talking about in the balloon ventilator. So we talk of something in a ventilator, you'll have a control called the tidal volume control. And if you put the tidal volume control to a certain setting, the ventilator starts blowing air into the patient when he breathes in. And this air is measured by a flow sensor. And if the flow is equal to a reference setting, which is given by the knob, the feedback loop is then considered to be stable. So it's locked. So the feedback loop tries to achieve a certain amount of flow, which is equal to the value given by the reference, and it does it by increasing the flange speed. And this is one particular mode in the ventilator, which is called the volume control mode. You have also a second mode, which uses a pressure sensor, which is called the pressure control mode, where instead of controlling the volume which is going into the ventilator, the patient, you control the amount of pressure that the patient has delivered to him. So there you use a pressure sensor. The second thing which I talked about is what you call a spontaneous mode, which is a mode where air is pushed in only when breathing is used as a trigger. So when the patient attempts to breathe, the flow sensor can sense his breathing, and making the attempt to sense his breathing can deliver a volume of air into the patient. So that's the second mode. So the breathing is generally sensed also by the flow sensor. Now, if you look at ventilators, if I talk about specifications for a flow sensor, there are three primary specifications. The first is what you call peak inspiratory flow. That's the maximum air a ventilator can push during inhalation. They talk about a figure called 150 liter per minute. And they talk about flow sensitivity, which is the ability to detect the smallest and faintest breath. So that's to detect breathing. What's the smallest change in flow that the ventilator can detect? In this case, they like a level of 0.2 liters per minute. And they also talk about Spec called the inspiratory time. So the inspiratory time is, they talk about the minimum inhalation time. So, when you breathe in, you breathe in anywhere between 200 milliseconds to 800 milliseconds. And if you were to make any kind of a control loop within this time, within your breath, so that you can detect the flow, and after that you can control the level of flow at a certain volume into the chest, all this has to be done in maybe anywhere between 200 and 800 milliseconds. So the response time, the transient response time of the flow sensor has to be faster than this 200 millisecond, which is the minimum value of this 200 to 800 limit. In the interest of time, we have made some setups to evaluate flow, and the setups really involve a 3D pipe. And so the 3D pipe is really and before I come to the 3D pipe, let me just first talk about what TI has as an offering. TI has a ultrasonic flow sensing solution, which is built around the MSP430FF6043 microcontroller. And basically, this is a microcontroller which is tailored to measure flow. It's used in water meters and it's used in gas meters. And what we have in this microcontroller is a transmitter and receiver placed in a pipe. And when air flows, the time of flight of an ultrasonic transmission, which happens between the transmitter and the receiver, changes. And if the time of flight changes with the airflow, you can measure this time of flight, and hence you can calculate the flow. So we have a an EVM along with which has got the microcontroller on it. To this EVM, you must attach two ultrasonic sensors. And then you have a GUI which comes in, which gives you all the information of the flow waveform and so on the computer screen. From our, we make a 3D pipe, which is just this blue section you see here. On the 3D pipe, on the corners, we attach the two sensors, and these sensors are then attached to our EVM. And from a fan, we generate air into this EVM in order to simulate a kind of a ventilator kind of an environment, which is generating airflow. And there's a big long 2-meter long pipe, and at the end of the pipe you have a customer or a patient who's breathing into this. So this is the setup we actually have in order to make flow measurements. And we also have a setup where we can make transient flow measurements. And transient flow measurements are very, very small variations, high frequency variations in the air, fluctuations in the air, which we also need to test. Fluctuations which might come as a result of breathing or snoring of a patient. So we take a speaker, a big full range, a woofer, and we give low frequency sine waves into the woofer. And as the woofer makes excursions, it moves the air in a very, very small manner. It fluctuates the air close to it, and that's picked up by the pipe, and then we can make our measurements. So we talk about the specs, and our main spec was peak inspiratory flow. It should be able to measure 150 liter per minute for breathing. So we took a fan, we blew it into the blew air from the fan into the flow sensor and into the pipe, and we increased the speed in steps. And this is the GUI reading, and this is the reading of the volume, the flow rate. And as you see, we are increasing the fan speed here, and you can see that the flow is actually increasing. At about 13.8 volts from the fan, we measured an airflow of 190.8 liters per minute, which is much better than the 150 liter per minute that we saw in the spec. And you can go further. There should not be any problem to do that. A second step is that we took this long 2-meter pipe, which I talked about here, breathing with a mask in the end of the pipe, and we were looking at the flow sensor to measure this. So on our GUI, here's what you see as the waveform of the pipe, of my breathing. So you can see the waveform of the breathing appearing as fluctuations in the airflow. This is the breathing in, which is a positive value. This is the breathing out, which is a negative value. So inspiration and expiration. And if you zoom into this, so you have this same thing zoomed in, where I'm trying to make the lightest breath, the whiff of the lightest breath I can make. And you can see that the whiff of the lightest breath is detected. And that the whiff to my mind is about 0.5 liters per minute. And the system is capable of getting such accuracy, 0.5 liters per minute. The third spec which we test for here is what you call inspiratory time. And I mentioned that with an audio amplifier, we were blowing air, fluctuations of air, and we were picking them up. So we were blowing frequencies from 20 hertz to about 100 hertz into the speaker, and they were creating very light air fluctuations of these frequencies. And we were picking the sensor, and the flow sensor is picking it up, and some circuitry was amplifying these very, very minute variations in airflow. Note that they flow down this 2-meter pipe and into this flow sensor. And there you can see the electronic, the scope shots of the airflow which is being picked up. So this is at 20 hertz, this is at 40 hertz, and this is at 70 hertz. So the airflow sensor can pretty much pick up airflow variations up to 70 hertz. And this should be enough for an inspiratory rate of 200 milliseconds. And if you look at the airflow variations in terms of, this can be looked at as a low pass filter, but with a bandwidth of 70 hertz, but a bandwidth of 70 hertz corresponds to a rise time of about 5 milliseconds. And this rise time of 5 milliseconds is more or less much better than the 200 milliseconds that you see. And yes, the 70 hertz here has an envelope, and that envelope is because of aliasing effects which are just starting to come in. because our sampling rate is around 150 hertz. So you start seeing some aliasing effects, which you start seeing coming in at 70 hertz. We did some demonstrations with the ventilator, and if time permits, I can try to run a video. So we made a kind of a ventilator demonstration setup. And this demonstration setup was really a fan blowing air into the sensor here, into a long pipe, into a human being. And we had our circuitry, which includes an EVM and some hardware circuitry you build here. And we had a system where the patient was breathing into the pipe. And the moment he was breathing in, the onset of his breath was detected by the system, and it was making the fan go at a faster speed. So the moment he was attempting to breathe, the fan was starting to go at a faster speed, and that's really the very premise of the spontaneous mode of a ventilator. So in every term, this is a very elementary form of a ventilator which has been set up here. I can, at the end of the presentation, I can try to take a look at the video if you like. We also did another ventilator demonstration, which is trying to accomplish a volume control loop in a ventilator. So a loop, a system where we take feedback from the flow sensor, close a volume of air into the patient, which is a certain amount. So you have a fan being driven by driving air into a pipe, and this is measured by flow sensor. So the flow sensor gives an EVM value, which is the analog value corresponding to the flow. And we have an analog circuit which gives a DC voltage, which is your reference voltage. And the job of this loop is to make this flow, which is coming from the air path, equal to this control voltage. So if the flow is less, then a signal goes to this MOSFET to drive the fan harder. So the system will lock till the time at a point where the flow is equal to the control voltage that you give. So if you do things like blocking the pipe, then the loop will try to blow harder and harder and harder till the time it reaches the edge. But this is again the second functional demonstration of how a ventilator works. So as I mentioned before, the summary of the specs is we could get a peak inspiratory flow of 150 liters per minute, very good flow sensitivity. We can detect the lightest breath. We can also the inspiration time is between 200 to 800. It's about 5 milliseconds. We can detect an inspiratory time of 5 milliseconds. So this is very interesting because there are applications where you have two flow sensors in a system. For example, a ventilator can have an inspiratory and an expiratory flow sensor, and we can, with one MSP430 microcontroller, run both the sensors. So you can have a single MSP430 FR6043, and you can run both the inspiratory and the expiratory flow sensor with the same MSP430, and so this can really give a very cost-optimized implementation for a ventilator. So this is something which just has to be kept in mind. So I think more or less I would say in terms of the transducers, we have a Chinese transducer which we prescribe, which is a 200 kilohertz transducer, which you more or less that was really what we had. Sorry to run through it very quick. In the interest of time, we had to run through it a little quick, but that's more or less what we had on flow sensing.
All right. Thank you everyone for joining in.